Okay, welcome to lesson number 7. We're still looking at quadratic equations, and now we're going to look at the discriminant. Okay, so this is the only time I'm going to allow you guys to discriminate in class, is when you're looking for the discriminant. All right, now let's examine what we need to do here. Find the roots of the quadratic equation x squared minus 8x plus 12, and that's equal to 0 by each of the following methods. First of all, by graphing. And so we need to graph this equation, x squared minus 8x plus 12. We're going to graph this, and then we're going to get something that looks like that. So it's crossing at 2 and 1, 2, 3, 4, 5, 6. It's crossing at 2 and 6. Okay, so we're going to say our x values are here and here. And then it looks like we have a minimum value of 1, 2, 3, 4, of negative 4. Okay, so it's somewhere down there. All right, so I'm just going to draw this graph looking like this, and we're looking for the roots. And so I know the roots here are going to be at, let's quickly look here. Let's look at this, my graph. X equals 2 is at 0, and x equals 6 is at 0. So yes, my roots or my zeros are 2 and 6. Now let's solve by factoring. X squared minus 8x plus 12. This is one that we can factor by inspection, eh? And so if we are factoring this by inspection, let's see, I need a number, 2 integers that are going to multiply to give me negative 12, or sorry, positive 12, and add to give me negative 6. And so I'm going to have, or negative 8, not negative 6. I'm going to have negative 2 and negative 6 here, and that is going to equal 0, which means my x values are 2 and 6, just like before. And by completing the square, so if we have, again, this, we're using the same equation for all these, by the way. So if you want to work ahead, you can do that. But we're using this equation, x squared minus 8x plus 12 is equal to 0. And if we're completing the square, remember that we want to take this term here, and we want to take the term half this and double, which would be 16. And if we're completing the square, we want to subtract 16 and add 12. And then this term here, we need to find the perfect square of. And so the perfect square is going to be x minus 4. And that's going to be squared. And then we just simplify out here. So we're just left with negative 4, and that is equal to 0. Okay? Now, in order to solve both sides, I'm going to have x squared is equal to positive 4, if I just bring that over there. And I square both sides, I'll be left with x minus 4 is equal to 2. If I take this, and I did that by taking the square root of both. And so if I bring, and this is plus or minus 2, by the way, because I didn't know if that was negative 2 and negative 2 to give me 4, or positive 2 and positive 2 to give me 4. And so if I subtract or add 4 to both sides, it's going to be left with 4 plus or minus 2. And so if I have 4 plus 2, I'm left with 6. 4 minus 2, I'll be left with 2. And now we need to use our quadratic equation. Okay, so x is equal to negative b plus or minus b squared minus 4ac divided by 2a. Now we know that our b values are going to be negative 8, and since it's a negative, we're going to have a positive 8, plus or minus negative 8 squared minus 4 times 1 times 12. And that's all divided by 2 times 1, or 2. And so we're going to have 8 plus minus 64 minus 4 times 40 is going to be 16, plus or minus 16 divided by 2. And this is going to be 8 plus or minus 4 divided by 2. And so we're going to have x values equal to 8 plus 4 is 12 divided by 2 is 6, and 8 minus 4 divided by 2 is 2. Okay, so that's how we solve it using 4 different methods: graphing, factoring, completing the squaring, and the quadratic formula. Now, each of these are appropriate at different times, which means that we can't always use all these methods all the time. Right? So if we want to solve something by factoring using inspection or decomposition, then this is only going to be appropriate when the equation is in general form and we can be factored, and so when it's in general form and can be factored, if there's a product of, if there is a product of two binomials. Okay, so if there's a product between our C value and our A value, and a sum between our middle term and end terms. Okay, so the quadratic formula, well, we can always use this actually. This is always appropriate. Always appropriate to use. So we can, that'll work with everything. But especially when something's impossible to factor. By completing a square, this is appropriate when in standard form. Standard form, that's really when it's appropriate. And then by graphing, this is also always appropriate. Always appropriate, but you won't always get exact answers. Okay, so that's the only disclaimer for this, is not always exact answers. So that's especially if the roots are irrational, and so like root 3 or something like that, you're not going to get an exact answer. Okay, so let's look at what we are doing now. Form a quadratic equation and solve. Okay, so if I'm going to form a quadratic equation, basically I need to multiply it all by the same value. So if you notice here, I have a squared and I have a on the bottom, and so that's a weird looking quadratic equation right now. So one thing I can do, if I multiply them all by 1, and in this case 1 being a squared, then I can get rid of all this a on the bottom. I get rid of this a and that one there, and I'm going to be left with, and actually I'll get rid of that too. And so I'm going to be left with 2 plus 3a is equal to negative a squared. Okay, so what I did was I multiplied each of these values by a squared. Right? And so that doesn't actually change the equation. And so now what I'm left with, if I rearrange this and set it equal to 0, I'm going to be left with a squared plus 3a. I'm going to reorganize it in a way I'm used to seeing, and that's equal to 0. And now this is something that we can just solve by inspection, right? Like if we want to have a product of 2 and a sum of 3, then I'm going to use a plus 2 and a plus 1. And then we have our values of negative 2 and negative 1. Okay, so let's look at investigating the nature of the roots of a quadratic equation. All right, so let's fill this. Insert the missing values of equation 1. So if I have x squared minus 6x plus b is equal to 0, then if I insert these missing values, this is going to be negative 6 squared here minus 4 times 1 times 5. We can put this in our calculator. We're going to have negative 6 squared minus 4 times 1 times 5. We're going to have negative, that's not right, 36 minus 4 times 1 times 5. We're going to have 16. Okay, that'll be plus or minus 4. And so if we have minus 4, then we're going to have x is equal to 5 and x is equal to 1. Okay, and so if we look at this graph down here, this is exactly what we're told as well, right? We have a value here at 1, and we have a value at 5. So those are 2 roots of our equation. Now let's look at the second one. And I'm going to pull this down. There you go. So if I fill in my quadratic equation again, I'm going to be left with negative 6 squared minus 4 times 1 times 9 this time. And negative 6, that's going to be added to these 0. So it's going to be 6 plus 0, 6 minus 0. And so my roots are going to be 3 and 3. Right? And so if we look at our graph, our roots are 3 and 3 because it doesn't actually move, right? Now let's look at this next one. X squared minus 6x plus 13 is equal to 0. Again, we're going to fill in what we have. We have negative 6 squared minus 4 times 1 times 13. And when we add all this up, we're going to be left with negative 36 minus 14 times 13, 36 minus negative 16. We're going to have negative 16. Okay, so we can actually take the square root of a negative number. So in this case, the roots are not real. Okay, they're not real because you can't take a square root of that negative number. Now let's see what this means. All right, so if we're working with the roots of a quadratic equation, and remember those represent the x-intercepts of the graph of the function. And so the roots of a quadratic equation, they can be said to be equal or unequal, real or non-real. And so if we consider these graphs, here we had roots that were not equal, but they were real, right? They're not the same as each other. This is a 5 and that's a 1. So they're not equal, but they are real. Now here, these ones are equal. They're both 3, and they're both real. They both exist on our graph. And this one, were non-real, and so they just don't even exist. Well, they exist, but they're just not real. Okay, so in graph 1, the roots of the equation x squared minus 6x plus 5 are real and unequal. They're distinct. In graph 2, the roots of the equation, they were equal and they were real. And then in graph 3, the roots of the equation were both non-real. And so the nature, and this is where we get to the discriminant. Okay, so this is the only time I'm going to let you guys discriminate in math. And the nature of roots of a quadratic equation can be determined without actually solving the equation or drawing its graph. The number b squared minus 4ac, which appears under the radical symbol in the quadratic formula, can be used to discriminate between the different types of roots. And so this is called the discriminant. So if you remember what your quadratic equation looks like, which you should all remember forever, your quadratic equation looks like this, right? Okay, so your quadratic equation looks like this. Now, if you have this is the discriminant. So this part is what goes inside of your quadratic equation, okay? So this is known as the discriminant. And so again, we can solve what the nature of the roots are going to be, whether or not they're going to be real or equal or non-real, by what that discriminant is going to be. Okay, so let's see here. Let's complete the table using the calculations from the investigations on the previous page. So let's see what our roots were here. For our first equation, our roots were 5 and 1. 5 and 1. So they are real, but they're unequal. They're not the same. And so when we had, for the discriminant here, they added up to be 16. And that was positive, right? Positive 16, not negative 16. And this one here, our roots were 3 and 3. They were real, and they're also equal, which means they're the same. And on the inside we had a 0 with that one. And then down here, there were no roots, they're non-real, and our discriminant was negative 16. That was a negative number. And so judging from that information, what can we determine? Well, let's see. If the discriminant b squared minus 4ac is equal to 0, then the roots are real and they're equal. Okay, so that was this case here. If the roots are greater than 0, which they were 3 and 3, and they're equal to 0, then the roots are real and equal. Oh, that was equal to 0. Sorry, so if the discriminant was b squared minus 4ac and equal to 0, then the roots are real and equal. So that's what we had here. If the discriminant b squared minus 4ac is greater than 0, so not equal 0, but greater than 0, then the roots are still real, so this one here, but they're unequal. And if we have a discriminant that is less than 0, so negative 16, then the roots are non-real. Okay, so maybe just pause here and just take a time to process this new information for yourself. Okay, and we're going to move on to this page here and determine, and all we want to do is determine the nature of the roots. So we want to do this without solving and without graphing. So we want to see, just like we did over here, only using the discriminant, what the nature is of those roots. And so I'm just going to do the first one, and then you guys can do all the rest yourselves. So here my a value is going to be 6, my b value is going to be negative 1, and my c net value is going to be negative 1. So if I have something under the square root, we don't even need the square root this time. We just need our discriminant. Okay, so b squared minus 4ac is going to be equal to negative 1 squared minus 4 times 6 times negative 1. This is going to be equal to 25. And so remember, if it's above, if our discriminant is above 0, then our roots are real and are unequal. Okay, so I'm going to say that the roots are real and they're unequal. Okay, now I'll do one more for you. How about let's do this one, just because it looks a little different. Now, if I have x squared plus 16 equal to 8x, then we're gonna have to switch this around to something we're used to seeing. We're gonna bring that to the other side, and this is gonna be plus 16, and that's equal to 0. Okay, so a is equal to 1, b is equal to negative 8, and c is equal to 16. Okay, so let's plug this into our discriminant, b squared minus 4ac. And so this is going to be negative 8 squared minus 4 times 1 times 16. And we are going to have a discriminant of negative 8 squared. It's going to be equal to 0. And so if it's equal to 0, remember that our roots are equal and real. And I said that backwards, but it's okay. You kind of get the picture. And for this one here, once you solve, you should find that this one up here is non-real roots. Okay? Now let's look at these next questions. Determine for what values of m the quadratic equation x squared minus 8x plus m has real and distinct roots. Okay, we want to know when it's going to have real and distinct roots. So what we need to do is just plug in what we have. a1, and we have b is equal to negative 8, and c in this case is equal to m. And so if we're plugging this into our discriminant, b squared minus 4ac, then I have negative 8 squared minus 4 times 1 times m. And we're going to want to solve for m here. This is going to be 64 minus 4m. And if we want to have real and distinct roots, then we would say that 64 minus 4m 64 minus 4m would have to be, if we want to have real and distinct roots. Where'd that page go? Oh, it's right here. So if we want to have real and distinct roots, remember that we want to have real and unequal, distinct. We want to have something greater than 0. Okay, so we're going to set this greater than 0. And if we are solving for an inequality, remember that we're going to bring this to the other side to solve for this 4m. And so if we bring the negative coefficient on either side, you are still going to end up flipping this inequality sign. So it'll be negative 4m minus 64. If I divide by a negative, I'm going to be left with m, and I'll flip that sign if I'm dividing by a negative. M is less than 16. Okay, and so my value of m has to be less than 16 if it's going to have real and distinct roots. Okay, now if I want to have real and equal roots, then this b squared minus 4ac needs to equal 0. And I already solved what the first part when it was 64 minus 4m is equal to 0. Now if we solve for m, then 64 is equal to 4m divided by 4. M is going to be equal to 16. So if we want to have real and equal roots, then m has to be equal to 16. Now let's see if we want to have non-real roots. B squared minus 4ac is less than 0, remember. And so 64 minus 4m is less than 0. If I bring this to the other side, I'll have negative 4m, negative 64, and m must be greater than 16. Because remember, if I divide by a negative, this inequality sign is going to switch around. So there you have it. Those are the answers for class example number 5. All right, so let's do these next few, and then you can do your assignment. So state a condition for b squared minus 4ac so that the equation ax squared plus bx plus c is equal to 0 has real roots. So remember, if we want to have real roots, then oh yeah, I keep doing this on this page here. If we want to have real roots, then we have to be at least greater or equal to 0. Okay, so that's the one condition that has to be met, is that our discriminant has to be greater than or equal to 0. Remember, it can't be less than 0 because that would be non-real. Okay, so given that the equation ax squared plus bx plus c is equal to 0 has real roots, state a condition for b squared minus 4ac so that the roots are rational and irrational. Okay, so if we want them to be rational, then well, let's see what happened here. Both times these were rational, right? And we had a perfect square. Okay, so if we have a perfect square, it's going to be a rational number and not a non-real number. And so 0 and 16 were both perfect squares. So if we have our discriminant is a perfect square, then our roots are going to be rational. But if they're irrational, then our b squared minus 4ac is not going to be a perfect square, or a square at all. Now, let's see, show that the roots of the equation m minus 2 times x squared minus 3m minus 2 times x plus 2m is equal to 0 are always real and rational. Okay, so this here is going to take my value of a, this will take my value of b, and this is going to be my value of c. This is going to be fun. So b squared minus 4ac is equal to negative 3m minus 2 And we are going to square this minus 4 times a, which was m minus 2 squared. M minus 2, or not squared, but just m minus 2, and my c value, which was 2m. Now, if I expand this equation, I'm going to be left with this, which is the perfect square, which is going to be 9m squared minus 12m plus 4 minus 4m minus 2 is going to be 8m, right? So 8m times m minus 2. So I'm going to do that one first, and then I'm going to do these two. So 9m squared minus 12m plus 4 minus 8m squared plus 16m. And if I gather my like terms together, I'm going to be left with m squared, 9m squared minus 8m. I'm going to be left with 4m and positive 4. And if I write that as a perfect square, I'm going to have m plus 2 squared. And so there's a perfect square, right? So since this is a perfect square, it's going to be real and rational. Perfect square.